Alternating current fundamentals. Number 4, capacitors, inductors, and transformers.
In the last part, you saw how alternating current can be represented using waveforms called sine waves. Amplitude and frequency were described. You saw that AC and DC values can be correlated by understanding the difference between peak and RMS voltages. In this video, 3 devices that play important roles in AC circuits will be examined: capacitors, inductors, and transformers.
The basic construction of each device will be investigated, along with their schematic symbols and units of measurement. You'll be introduced to the basic principles behind their operation.
Let's get started. You've already seen that resistors serve the same basic purpose in AC circuits that they do in DC circuits and are used just as frequently.
While the voltage across and current through a resistor in an AC circuit constantly change over time, the Ohm's law relationships among voltage, current, and resistance still hold true.
But the devices you'll see in this video have characteristics that are most fully exploited within an AC circuit. Their full operation relies upon the varying voltage and current that is present in AC.
Let's examine capacitors, inductors, and transformers, starting with capacitors. If you could see beneath the cover of virtually any electronic system, you would find capacitors of all shapes and sizes. Look inside this unplugged radio, for instance. Capacitors can be found in the power supply circuit, in the tuning circuit, and in the amplifier circuit. Regardless of the particular application for which they are used, all capacitors exhibit certain common operating characteristics.
The basic job of a capacitor within a circuit is to store an electrical charge. Let's see how a capacitor is constructed in order to accomplish this.
A simple capacitor, or cap, is composed of 2 metal plates which are conductive. The plates are parallel and are separated by an insulating material called a dielectric. Different types of capacitors use different substances for dielectrics, but regardless of the substance used, it is always within the dielectric that the charge or electrical energy is stored. Each plate of a capacitor has a lead attached to it. These leads are used to connect the capacitor to an electrical circuit.
Let's see how a capacitor functions step by step. First, in a simple DC circuit.
The 2 rectangles labeled L and R at the top of the circuit represent a cross-sectional view of a capacitor's plates. In this case, they are separated by a dielectric made of air. At this point, each plate contains an equal amount of free electrons. The capacitor is in a neutral or uncharged state. But when the switch is closed, the battery voltage causes electrons to flow in the circuit. The positive terminal of the battery will attract free electrons from the capacitor plate on the left, labeled L. At the same time, an equal number of free electrons are deposited on plate R on the right. As plate L loses electrons, plate R gains electrons. Plate L becomes positive with respect to plate R because it has a deficiency of electrons.
It's important to realize that during this process, free electrons do not pass through the dielectric because of its insulating characteristic.
Free electrons travel through the connecting leads, source, and switch only. This forced movement of electrons from one plate to another by a voltage source is known as charging. The electron flow is referred to as a charging current. The applied voltage will continue attracting free electrons from plate L and forcing them onto plate R until the voltage across the capacitor, labeled E sub C, equals the maximum voltage across the source, labeled E sub S. At this point, the voltage across the capacitor has the same polarity as the applied voltage. Current ceases to flow because there is no longer a difference of potential between the voltage source and the capacitor. When the switch is opened, the charged capacitor is disconnected from the voltage source. But within the capacitor, there is a negative charge on one plate and a positive charge on the other, causing an electric field to be developed in the dielectric between the plates. The arrows represent the electric lines of force which make up the electrostatic field. The strength of this field is directly proportional to the potential difference, or voltage, between the plates.
Stop the program and complete activity number 1. When finished, continue watching the program.